University, but that particular day actually.
Yeah, I attended that talk when you gave that one. Yeah, but after some time you don't listen to don't look at the slides, you just listen to the persons. Yeah, so people are slowly joining. Just a couple of minutes more and we'll start.
Yeah.
How now you guys are planning to go somewhere after this?
No. Actually, what happened was we were supposed to go somewhere, no, from here, but then I got little bit cold yesterday because of too much. That room has too much of AC, and we are non-stop. We are sitting there, so I am fine. So we thought that we'd forget about going anywhere.
Yeah, this change of weather also. Hyderabad is pretty dry. Hyderabad like Pune, right? Hyderabad, that dryness is like Pune.
Hyderabad is very hot here. Daytime is
Very hot.
really hot, very hot. Of course, there is central AC and everything is there. The facility is very good. You have come here, IIT Hyderabad?
I have not gone there. No, not yet. No. I went to Hyderabad last time. That was quite some time back. This time actually I was very keen. But you know what happened? In Odisha, they wanted to hire some faculty after a long time.
Utkal University?
These are all college lecturers.
Okay.
I know there were some Supreme Court problems. Now they're hiring them in a big number.
Achha.
So what to do? Say they requested that some of you should be there, otherwise candidates will not be selected. The kind of initiative. Remember this boy? Durga's classmate was talking about.
Kiranma?
Durga's classmate. Remember that this who is an administrator right now?
Ashok.
Yeah, Ashok. The same initiative is now being implemented.
Yes.
Yeah. So I think we can start.
Yeah.
So it's let me introduce Professor Bishwajyoti Dey, my classmate and dear friend from Pune. He did his PhD from Institute of Bhubaneswar, where I was his classmate, and it was such a pleasure. His deep insight into statistical physics, nonlinear dynamics, and in physics in general. And it's a pleasure always to discuss with him. Subsequently, he went to Ahmedabad, I think IPR, if I remember correctly.
Yeah.
And then Pune University, and he has been there in Pune University. I can see he has established a school. You see, this polar atoms, which is a combination of nonlinear dynamics plus quantum mechanics of at very low temperature, has been his forte for quite some time. Lot of original contribution and in close connection to the experiment. That is what one sort of feels very proud of. That sometimes you always look for some experimental confirmation, but you see with Pratap Rai Chaudhary, his model of these two Vortex melting has found experimental verification, which is a very remarkable achievement. And with Vortex binding, and this rotating VC, spin models, and the 1D integrable systems, which are all now coming into play in the quantum domain. He has tremendous experience and original contribution. See, for example, this Hubbard model, the spin models have been actually the ones which is being proposed for quantum change, both for storage of information and also using the quantum correlation for quantum computation. And vortices are, of course, another areas which is evident the moment you come to 2D. So this 2D is a very very little explored. Now experiments are there coming out. So now so let's say here quantum vortex chase is rotating Bose-Hubbard model. Hopefully some of you students who are around will think of some kind of applications in quantum domain. So Professor Bishwajyoti Dey, the stage is yours.
Okay, thank you, Prashant. Let me just start. So I'll be talking about quantum vortex states in rotating Bose-Hubbard model. And I'm from Pune University, as Prashant mentioned. And can I go one page up? I have to go one page. Just
yeah, it's moving. It's moving.
But it's moving too fast.
Okay.
Yeah. Yeah.
Yeah.
Now I can start. So as we know that simulation using quantum cases on two-dimensional optical lattice allows studies for various strongly correlated problems nowadays, for which most important thing is that you cannot have conventional methods. Okay, you cannot, neither you can do the experiment uh, on this kind of thing. For example, one-dimensional system, strongly correlated system, those kind of things are experimentally not available. But we can do this thing at least in simulated model using what is called as the Bose-Hubbard model. Okay, so there are various important issues here. So, for example, for the first time, it was introduced by Fisher, where they studied the effects of repulsive two-body interaction and the pinning by optical lattice potential. So, basically, the optical lattice potential is the most important here. Like, for example, in strongly correlated system, one example that we have are 3D transition metal, where electrons are localized in the lattice points, and then they can also tunnel to the nearest sides. And if the tunneling is there, we say that it is what is called superfluid. If it is not there, if the lattice potential or whatever is very strong, then we can superfluid mode insulator. So these things were known and theoretically, but nowadays it has been realized experimentally. For example, in 2002 Nature paper, they have done outer pole atoms in optical lattice by Grainer-Ritter. Okay. Now what has happened is that study of Bose-Hubbard model on different lattice geometries, in particular the triangular lattice, Kagame lattice, Weave lattice, these are all very recent importance. Okay, so they give additional interesting physics here, and that's why we are interested to know what is the Hubbard model on different kind of lattice geometry, and that's what we will be talking about here. For example, experiments on cold atoms succeeded in realizing the celebrated topological Hamiltonian model on a Hamiltonian optical lattice. And so you have to rotate, for example. What we have to do is that the other studies involve density matrix renormalization group study. And so it shows that there are very rich ground state phase diagram with super solid phase. So this is on a triangular lattice. Okay. On top of it, if you put also a harmonic trap, then this also gives a very other new things. For example, the effect of trap potential on superfluid mode insulator transition in the Bose-Hubbard model have shown very different behavior, like locally incompressible mode insulating behavior in 1D chain. Okay? So harmonic trap potential actually introduces space inhomogeneity in the system. That is the only thing. Similarly, one can introduce rotation in the Bose gases by rotating the optical lattice itself. That will allow us to study new things, which is called as the quantum vortexes. So it is similar to like our what we do continuum system, Gross-Pitavsky equation we solve and get the vortices, but that is weakly interaction system. In this case, what we are going to study is that do we have vortices in strongly correlated system? And if you have, then how does it depends on different geometries and all kind of things, okay? So why do we want to study this? Because particularly we want to study about the vortices, soliton, quantum fractional effect, etc. Okay, so that is the motivation of the talk. So most important, as I say here, that if you want to make a strongly correlated lattice, then you should have an optical lattice. So basically the core atoms are transferred to the optical lattice. So optical lattice, as I've shown in the figure, it's a periodic arrangement of intensity pattern, which are made by lasers. And BEC mounted, BEC, those atoms you can see there's round ones, those are the BEC mounted on optical lattice, okay? So these are like electrons moving in a periodic potential of ions, okay? So that is the advantage. So advantage is that it is possible to control the interaction, which is not possible with the electrons conventional cell. This is the idea why we want to go here. So advantages condensate approach is that it is possible to control the interaction, which is not possible with the electrons in conventional solid. So we can use phase spec resonance and all these things to make the interaction between the atoms, or we can make the depth of this optical lattice as strong as possible. So that means very strong interaction limit we go. So as I said here, strong interaction limit either by fetchback resonance or turning up the lattice potential. So this is what we do here. So for us, it will be a deep optical lattice. So the atoms will be like electrons in 3D transition matter, where in the D level, the electrons are localized mostly. So now let us see how to do it experimentally. Strongly interaction boson in a two-dimensional optical lattice. Such a system corresponds to a rotating lattice potential imprinted on a trapped Bose-Einstein condensate. So basically what you do is that you have a Bose-Einstein condensate, and then you pass laser light through a rotating mask as I've shown in the figure, and that mask will have the shape that you want to give, whether you want to have a lattice of particular geometry, say square, triangular, whatever. So we make holes into this mask and pass on the laser light. A lens focuses the resulting laser beam into the stationary trapped BEC. Lattice potential imprinted via the interaction between the laser and atom. So this is basically the what we call just a moment. Do you know how to go up a little bit? This is going up faster. So if I want to go down a little bit, shift it a little bit, then it is going to the next page. But very sensitive. Okay. So this is the experimental setup. Okay. Okay. Now let us do some theory. So first we have to do is that consider bosons in 2D optical lattice which rotate about the z-axis. So basically, 2D optical lattice which rotate about the z-axis. So our lattice will be rotating. The bosons are interacting via an effective two-body contact potential. So now we want to do some kind of many-body theory. So what we do is that we do our standard, just like we did for Grasp-Pittelowski equation derivation for the weakly interacting system. For strongly correlated system also we do the same thing by using a bosonic field operator, which is expanded in terms of creation and annihilation operator for boson. A is the annihilation operator for the bosons, and W is the linear function. So that makes it localized at the IIT site, and it's a bosonic operator. A is the bosonic operator. So that makes it different from our standard weakly interacting system, that instead of the free particle wave function, we use a linear function which is localized. Now these linear functions of course satisfy all the properties, like two linear functions are orthogonal, localized to two different sets are orthogonal to each other, and all this satisfy. They satisfy this property. So this field operator satisfies the usual bosonic correlation, commutation relation, which is given here. And then in the rotating frame, the Hamiltonian can be written in terms of bosonic field operator as this. Now this is our standard procedure where we have the field operator here, and these are the single particle terms which we have put here. So LZ is basically given by our standard P cross S, P cross X. So X derivative minus Y derivative. Okay. So this is our bosons on a rotating optical lattice. But now the rotational part, as you can see, it becomes very interesting. When we expand it in terms of the second quantized form, we notice that this has got what is called as the hopping term. Okay, this hopping term, this gives rise to driven hopping term. Okay, that means we are driving it because of we have put it on a rotating optical. So the rotation basically drives the bosons from one side to another side. So this will be controlled by what is called as the parameter Kij. Okay, Kij, which is depends on the position of the particles, which is on the lattice, and beta is a overlap integral. Okay, overlap integral, which is this one. So if the overlap integral is very small, then of course there will be no transition of the particle between the from one side to another, even in presence of rotation. But this is what happens in Hubbard model. Even for the other term, which is T here, the usual kinetic energy term, that also has Wi, Wj. So if there is not sufficient overlap, there will be no tunneling. So here also it is the same thing. So now what we have that in addition to the usual kinetic energy term, that we have the T here, rotation introduced and the rotation term, transition term from what is called as hopping term, which is given by, which depends on omega actually, where omega is the rotational frequency. All right. Now, So if I substitute everything again, the Hamiltonian now in presence of rotation becomes like this. So you can see that there is a term which is a rotation. Now, if you compare the first and the second term, you can see that it has got more or less similar kind of jumping from between one side to another, from one side to another side. So A dagger AI, A dagger J in the first term, and then so fast. And then this term is similar. So these are the two hopping terms, and I have this is the Coulomb interaction term. So there is a competition between these two terms, the hopping term and the Coulomb interaction term, which tells us that giving rise to what is called the Mott insulator or superfluid nature. If the Coulomb interaction is small, then we have superfluid. If it is strong, then we have the Mott insulator. So this is our standard thing. So this is the usual Hubbard model, but we have just put on a rotating optical lattice. And the idea is to put on a rotating optical lattice is to obtain the vortex in this 2D lattice. So now again, this is the geometry, basically. So this is the geometry.
Yes, now it is. There is black box on the top.
So, I've cut it off.
On the bottom, could you also please remove?
Okay, well, how to remove that? Yeah.
Now it's okay. Another box appears.
Yeah. Now it's okay?
Yeah, it's okay.
Perfect.
Yeah. Yeah. So this is our Hamiltonian. So basically what we have done is that we have done additional effects of co-rotating harmonic trap. As I said, that harmonic traps give interesting physics, both in 1 dimension as well as 2 dimension, and also 3-body interactions. Okay. So this is a generalization to see that what happens in general, because why we need a 3-body interaction, because if I have a dipolar kind of boson atoms, then they will have some kind of long-range interaction. So we try to incorporate here. So what is new here? New here is that this term, the first term and the second term, third term is usual Hubbard model. Then we have added a rotation which gives rise to the second term, which again makes something like a transition from tunneling from one side to another side, just like in presence of kinetic energy. Then I have a 3-body rotation here, the fourth term, and then I have the trap, which is, you can see that the trap depends on the side, which means that it is not, it is inhomogeneous. And then I have next nearest neighbor interactions, which is 3-body interaction is on site, and this is the next nearest interaction. So this is the most general model that we have studied, including everything, and we call it as extended Bose-Hubbard model. Okay. Now what we have done is we want to see what is the effect of the trap, inhomogeneous trap. Okay, because that produces what is called inhomogeneity in space. So instead of, if I take just I square, which is called the harmonic term, then of course I'll get a trap which is centered at, but I want that, by choosing this delta, what we do is that we try to put this optical lattice, center of the optical lattice, which is not on the lattice side. If I don't put this C and delta term, then they will be on the lattice side itself. So it is certainly not favorable. So we try to put it on the off from the lattice side. So I will shift it by this one. This is something like a shifter oscillator. So now here, there are important terms here. Lambda tells you the measure of the curvature of the trap. How big is the trap? I will show you a figure. And delta tells you how much I have displaced from the center of the, C is the center of the 2D lattice, and delta is the displacement from the center of the lattice. The advantage of this trap is that I can choose my delta of the center of the lattice on one side of the lattice in 2D lattice, say third quadrant or second quadrant, something like this. If I break the 2D system into 4 parts, and then I will see what is the effect of this thing on the vortices in the system. All right. This is better. So this is our realization of Bose-Hubbard model and optical lattice. So this is my full Hamiltonian, and so this is the picture actually. How do they do? So I have this optical lattice which is going up and down, and the depth of this optical lattice is V0. Okay, so depth of this optical lattice is V0, and I can control it by adjusting the laser beam. So for a strongly correlated system, I make this V0 to be quite deep actually. Then the atoms or boson atom goes from one side to another side, with a probability J, okay, tunneling probability. In my notation, it is T here in my Hamiltonian. And then, but once it goes to the other side, then there will be Coulomb repulsion between the two atoms and giving rise to an energy increase in the system by U, okay? And that is the Coulomb interaction term. Now this, you can see at the bottom, there is a harmonic trap here, So this is made as flat as possible, but how much flat and all, it can be controlled by what is called as the parameter lambda. And where will be the off-centered and all these things probably be controlled by the parameter delta. Okay, so you can see that this epsilon, which is here, now depends on the lattice size. Okay, so different sizes we have this, and that's why it is off-center energy. Basically, it changes the energy of the system by some amount. Okay, so this is basically the geometric picture for us. So let us go ahead. So this I have told already. So rotation introduces hopping, and then we can add these two together. Okay, the hopping term due to rotation and hopping term due to kinetic energy, we can combine them together to make a new side-dependent hopping parameter, which is complex now. So this complex hopping parameter can be realized by artificial magnetic field, and that has already been done. Okay, so everything that we want to do here can be tested experimentally, depending on the system, like 1D, 2D, or what geometry we want. All right. So once we have fixed up the Hamiltonian, we have to now go for the state of the system, because you have to calculate certain quantity. The eigenstates of the Hamiltonian can be written in terms of the number of basic states, just like psi. This is our standard many body theory with certain amplitude, and N1, N2 are the occupation number at different lattice sites, and N is the total number of lattice sites. Okay, and the total number of particles in the system is given by summation over Ni, and that is N. Now, how do we calculate? What do I calculate? First, I can use numerical exact diagonalization method, and we consider different lattice of different geometry. And what I calculate is actually the exact ground state eigenvalue and corresponding eigenvectors. I need both of them, and also in some cases we can also use the first excited states. Okay, so this is exact. Whatever we are calculating here, simulating here, these are exact because it's a numerical exact diagonalization method. So what is this method? In this method, a Hamiltonian matrix is constructed corresponding to the given Hamiltonian using the basis states. Okay, and diagonalized to find the eigenvalue and eigenstate of the given Hamiltonian. So basically what you have to do is then in the number particle representation that Ni I have written here, you have to find out all kind of possible distribution of the number of particles. All kind of distribution of the possible number of particles, and give the basis state, like 1, 0, 0, 0, 1, 0, 2, 0, 2, 1, 0, like that. For bosons, you can imagine that we have many more states compared to the fermions, because bosons occupation number is 0, 1, 2. Even for fermions, I can have 0, 1, 2 if I put up and down spin. But bosons, I can put as many as I want. Okay, there is no restriction. So number of possible states for Bose-Hubbard Hamiltonian is very large. Okay. So once we have the basis states, in that basis states, we calculate the expectation values of H between these basis states and construct a matrix. We diagonalize this matrix to get the eigenvalue, and then the corresponding eigenvectors will give me the states of the system, okay, correspond to the ground state of first excited states. Now we can calculate something. So what is how to do the calculation? First, there is an unknown parameter in our problem. Beside the usual parameter of beta, T, U, W, all this, I have an unknown parameter, which is beta. So we realize that this beta is actually, numerically, people find it numerically, but we realize that we can do it by using the geometry of the lattice. Like, for example, we try to find that whatever lattice you choose, beta turns out to be greater or equal to Z. What is Z? Z is the coordination number. And beta is this constant here. So this Kij if you remember, this was the amplitude or probability of tunneling from one side to another side due to rotation. Okay. So for example, let me tell you, let us consider square lattice. If a square lattice of size L cross L, the 4-4 symmetry allows maximum L minus 1, that quantized vortices within the lowest span. So for example, if I have 4 cross 4 lattice, then it will give me only 3 vortices. Okay, so that is the maximum number of vortices it allows. So what we do is that as I increase the frequency, rotational frequency, the vortices enter the system one after another, and the phase winding of the condensate wave function increases in steps of 2 pi. Because for one vortex, the phase winding is 2 pi, and for L minus 1 vortices, the total phase winding is 2 pi times L minus 1. And the maximum phase difference between neighboring sides is pi by 2. All right. So now we can understand that as compared to the other continuum vortices, this is actually goes in terms of the lattice side between nearest neighbor. So we always talk about what is the current between the nearest neighbor, what is the probability of transition between the nearest neighbor, what is the phase change between the nearest neighbor, and so on, because it's a lattice system. So now what I do is that I calculate this phase, okay, of the system, and then I vary with omega. Now, as I said, that there should be maximum values 3 vortices as in the system. So you can see that from that figure, these are plotted for various beta. Beta is not known to me, but I know it from this figure because I know that it has to give me 4 vortex. Okay, for a 6 cross 6 lattice, it should give me 5 vortex, 1 less than that, L minus 1. So now you see that if I take beta equal to 3, then I don't get 5 vortex. I get 1, 2, 3, 4. Okay. Then even if I take beta equal to 4.2, right, the green line, I don't get this 5 vortex. On the other hand, beta I can get about 4.9 gives me 5 vortex actually. On the other hand, if I take beta is higher than the coordination number, okay, then I get 10. Okay, for say beta equal to 10, we get more number of vortex. Okay, so the right number of vortex, that means I want 5, 1, 2, 3, 4, 5. That is 1, 2, 3, 4, 5. Okay, so this is obtained by knowing, from there I know what are the beta. So basically I do the calculation like this. I calculate the phase of the condensate, phase winding of the condensate, vary with omega for different values of beta, and find out for what values of beta I get the right number of vortex which is allowed. All right. So this is the way we fix vortexes. Now, to get some information out of it, this calculation, remember that we are only calculating the ground state of the system and the corresponding eigenvector. So whatever I do from here, I have to do it in terms of this thing. So this is the quantum phase transition where the ground state changes by changing some parameter in the system. Okay. So in this case, the ground state changes because I am rotating the system, and the change in the ground state means that it is a 1 vortex state, 2 vortex state, 3 vortex states, such that we have different kind of phase, okay, condensate phase, 2 pi, 4 pi, 6 pi, and so on. So first I say that we calculate 6 quantities here, okay. First of all, we use the open boundary condition and phasing factor less than 1. So this is what is our phasing factor less than 1 means number of particles will be less than the number of sides, okay. Half field cases when they are same, but here we are doing less than that. Okay. Remember that we don't have much choice because we cannot put too many particles in the system. We cannot make it very big size because the basis states increases in crores actually. So we have to have our some kind of we have to decide that how much particles I should shoot, what maximum size of the lattice, so that depending on the computation system that we have with us, we adjust. Okay, but still, so you have to use a minimum number of sites so that at least you get some information out of it. So first I calculate the ground state eigenvalues and eigenvectors. That is the standard. And from using this one, I calculate all the quantities. For example, I calculate normalized variance. So this gives information about the system phase like superfluid or Mott insulator or whatever it is, and define is like this, is basically a variance here. So if nu is 1, it represents coherent state, that means states with all phase same. Phase quiz state, these are phase quiz, numbers quiz states. These are the quiz states basically means that you are trying to, for those states, you are trying to reduce the uncertainty, okay? So for example, in terms of electromagnetic wave, photon, phase square states, we have a state where we have a localization with a very little change in phase. Number square stated that number distribution will be uncertainty in that will be very small. And single state is of course that. So knowing from this one, I know whether the system is Mott insulated or superfluid or so. So here is a picture here. I can show you that there's nu versus how does the nu varies with omega as I rotate the system. Okay. So now and this is the number of particles, 2 particles, 3 particles, 4, 5, and the lattice is 2 cross 2 lattice. Remember that this is just 2 cross 2 lattice. Okay. So it is 4 lattice sides. This is just an example. All the figures that I'm showing here can be generalized to higher lattice sides. At least we have checked up to 6 cross 6, up to that much. 2 cross 2 means 4 lattice sides. So if I have 4 particles, then it's half field. If I have more particles, then more than half field. And n is 2 means less than half field. Okay. So now you see that this coherent state, variation of omega changes the physics of the system, state of the system from coherent state at nu equal to 1 to more nu greater than 1, and for certain values of omega to nu less than 1. Okay, so this is the way it varies with as I change with. So basically the system ground state is changing as I change the omega values. Let us calculate now intersite current. This is a very important quantity. Okay, remember that vortices in continuum system is basically a density dip. There is nothing at the center, and it is like a tube, nothing at the center, and there is a current around that. Okay, discrete system is similar. Only thing is that I have a lattice, so I have a current which is going from intersite one side to another side, and that current is produced because I'm rotating the system, and of course because there is the standard tunneling T terms. So you see that Jij that I have written on top, because depends on these two tunneling term, one because of the T, which is the kinetic energy term, and this is because of the rotation. So both of them contributes. Okay. So what does it do? Jij, why do I calculate? Because it signals the approach to superfluid density. If Jij is non-zero, then I have superfluid phase, and if I have Jij is 0, then I am Mott insulated. Okay. So this is the idea. Now, what is happening here is that the total current is conserved at each lattice site. That means the outgoing current and inward current at every lattice site is 0. Okay. Similarly, I have another quantity, which is the current at the boundary of the surface. Why do I calculate that? Because to distinguish my vortex state from that any other state is not a vortex, I calculate the boundary of the current. Look at this figure at the last one, D. There is no vortex here. So what I do is that I keep on changing my frequency, omega. Okay. So omega 0.005, no vortex. There is a current between the sides and all this thing, but there is no current. I mean, what is that? The phase change and the total current, okay, should be 0 at the boundary. Look at, so when I put omega equal to 0.135, I don't get the vortex yet. When I put omega equal to 0.175, I still don't get the vortex, because you can see when I mean by I still don't get the vortex, what it means that there is some arrows which are still coming out. Okay, this is the vortex state. When I get a vortex, then you see that this is the current I was saying, the total current of the lattice boundary. This is the lattice boundary current. And the vortex is this anti-clockwise result. So this is the vortex between these four sides. How do I know that this is a vortex between the four lattice sides compared to this one? This is a closed current, and there will be a phase change. If you calculate the phase change between these four sides, you get exactly 2 pi. If it is a second vortex, then you get 4 pi, the third vortex 6 pi, and so on in multiples of pi. So we plot it with respect to the change in phase with respect to divide by 2 pi, and we get answer as 1, 2, 3. So this is the vortex state of a system. It's a 4 cross 4 lattice system with just one particle. Okay, so this gives a density distribution in the system, and so this is the current. Current is important actually because it gives other things also. Current is also useful to particle hole symmetry in the system. So what is the particle hole symmetry? That means if I have for a strong repulsive interaction, if I have one particle, and if I have one particle less than half field, that means one hole or one particle, then the physics or the quantity that I calculate should be similar. It is same. Okay, but for large. So now you can see that a repulsive interaction between the boson is expected to decrease the current flow as it makes it difficult for the particles to tunnel from one lattice site to another. Okay, so it will remain in one place. So particle hole symmetry for n equal to 1 and n1 less than 1, the current at the boundary lambda c for what is called for U very, very large than transition probability, it is something like a mod insulator, matches exactly. This is true for all lattice geometries. This is important because we find that this is true for all. That means there will be a particle hole symmetry. So what is this figure? The first figure is for a square lattice. Now, these are the different colors for different values of U. As I increase U to 1000, that means strong interaction. You can see that there is a particle hole symmetry. That means I have 4 lattice sites. In 4 lattice sites, I have 4, for half wave case, I have 4 particles. So one particle or one less than 4, that is 3, they have the same value. Okay, this is a particle hole symmetry. Now this is for rectangular lattice, this is for triangular lattice. So this is the particle hole lattice. So I can calculate this one from the current at the surface. Another thing that I want to calculate is the average angular momentum for the ground state, which is defined as del E0 by del omega. E0 is the ground state energy and omega is the rotational frequency. Okay. Now remember that in our continuous vortices, we also calculate average values of energy. But there, the LZ is quantized. Okay. So that's why I call quantized vortices. In this case, we see that L is not quantized, but I'll come to that. But before that, let us see that variation of LZ with rotation. Okay. Now this tells me that how vortices are entering the system. As I change my omega, then you can say that there is a jump in the angular momentum. So first jump, so this is a 4x4 lattice. So I expect 3 jumps. 3 jumps means 3 vortex. So at these values of frequency, 1 vortex is entered. And at this frequency, another vortex is entered. And this frequency, there is another vortex. Now from this figure, you can note out that if I increase the number of particles, it doesn't change the position of frequency. So this is the ground state energy change of the system as I change my omega parameter, and this is the quantum phase transition. But if you look at the values of LZ, they're high. Actually, in our continuum system of vortices, we should get 1, 2, 3. These are the values, quantized values of LZ. Okay. So does it mean that these angular momentums, what you call as the vortices, quantum vortices, are not quantized or what? This is not true actually. There is something else is quantized. Angular momentum of the system is not quantized due to discrete rotational symmetry of the lattice. Because it's a discrete system, it is not continuous. So LZ takes on non-quantized values, which shows that the energy eigenstates are not eigenstates of the continuous angular momentum. Okay, that we used to get for our continuum Grasp-Podolsky equation. However, since the discrete rotation operator commutes with the Hamiltonian of the system, for example, J, if you take a J-sided regular polygon, a rotation of 2 pi by J leaves the system invariant. Okay. So if I have a rotation operator, then I operate on a state, the eigenvalue is this, the eigenfunction is this. Now we see that this is true for m equal to 0, 1, 2, 3. Okay, so this is the quantized value. So there is quantization, but not the angular momentum is not concerned, but we say that this is called the quasi-angular momentum conservation. Okay, just like we have for transition operator, we do the similar thing. Okay, all right. So now, these are the things that happens when I have already told about these 3 things that I calculate. Entry of each vortex is indicated by the jump in LZ, boundary current, and the phase winding. Phase winding is easy. So you see that I have 1, 2, 3. Okay, so phase changes by 1, 2, 3 for the 3 words. This is a 4x4 lattice, so there will be only 3 there. Now for each same frequency, you see that there is a jump in the angular momentum also, but this is not quantized. And there is also jump in the current around the surface of the, on the boundary of the lattice. So at every stage, there is a jump in the discrete jump, showing that this is a ground state change in energy because of the change in parameter omega, and this is a quantum phase transition. Okay. But this is not completely true. It is true, but to a certain extent, if I take the attractive interaction between the particles, then besides these L-1 jumps, okay, if I have L cross at L lattice, then I should get L-1 jumps, because L-1 jumps means L-1 vortices. For each vortex, I have 1 jump. But if I take an attractive interaction between the particle, then we notice that beside this L-1 jump, there are additional jumps in LZ as well as in boundary current. For example, here. For example, here. So I can see that if I take a 2 cross 2 lattice, I should get one vortex. Okay. So, but you see that that means 0 to 2 pi, there is only one vortex between 0 and 2 pi. Okay. Because 2 cross 2 means 2 minus 1 is one vortex. So I should get only one jump. So this one jump happens in here, but in angular momentum, there are so many jumps here. Current also similar jumps are there. So what does that mean? Does it mean that since there are so many jumps, does it mean that additional vortices enter the system for repulsive interaction? The answer is no, because the phase still changes by 1. Okay, that means the vortex is 1. So intermediate steps are not the real vortices. Okay, they correspond to some kind of phase winding. This implies that the number extra jump do not correspond to entry of any new vortex in the system. Number of such jump depends on the number of particles, and for n particle there are n minus 1 extra jumps. Okay, this is for attractive interaction. Now for extra jump, why there is an extra jump is that because there is a, you see that there every discrete jump there are crossing of energy levels between E0 and E1. Okay, see there are so many crossings. So for each crossing there is a jump. So what is the crossing means? So here is the, for this problem I have to calculate the first excited state. So what is happening is that for certain values of omega, the ground state energy is first excited state energy is become either equal or less than that. So that become the original ground state. Okay, means the ground state in presence of rotation U1 becomes. Otherwise, it is like that. So you can say that vortices. Of course, we know that the excited states of the system. So this is the way it changes. But this is for attractive interaction. Then I calculate another quantity. As I said that I'll be calculating 6 quantities. So condensate fraction. So why do I calculate that? Condensate fraction is associated with the superfluid nature of the system. So what Penrose and Onsager had argued that for a Bose-Einstein condensate to be present, the single particle density mode with the largest eigenvalue must be macroscopically occupied. Okay. So this is what they had predicted. And we know that for continuum system, this is valid. For discrete system, what I have to calculate that, I have to calculate the single particle density matrix. Okay, so this is what is our single particle density matrix. And psi 0 is given by the ground state of the system. In that ground state, I calculate what is the single particle density matrix, just like Penrose and Onsager mentioned, and then find is the largest eigenvalue. Okay, the ratio of the largest eigenvalue of the density matrix and the total number of particles gives the condensate fraction. Okay, so if the largest eigenvalue is 0, for example, and then of course I will not get any condensate fraction. That means there is no condensation. So for lattice also this is valid. So what we do is that we examine the variation of the magnitude of the ground state condensate fraction as a function of rotational frequency omega. When the ground state changes, there is discontinuous change in the condensate fraction. As I said that as a change in omega, then vortices is centered one by one. As the vortices changes, there is a discontinuous change in Lz, lambda c, as well as theta, the phase. So that means when the ground state changes, the condensate fraction also changes. Okay, what does that mean? That means I might go from superfluid state to non-superfluid, or what is called as the Mott insulated state. Okay, so the condensate fraction decreases with increasing strength of the interparticle interaction. That we understand because it is not allowed to go to superfluid state. It is more like Mott insulated. So here is the picture of a condensate fraction. Now condensate fraction with attractive interaction. This just we have given for attractive interaction. So like the repulsive interaction, with attractive interaction, as we increase the attractive interaction, the condensate fraction decreases. That means it doesn't like it. So condensate fraction almost changes from 100% to 50% as you change the values of omega. Now these are the discrete changes. You can see that why these discrete changes? Because every time the ground state of the system changes, the condensate fraction changes, discontinuous angular momentum changes, discontinuous phase also changes. So these are the change. And here you can see that how does the condensate fraction. So if the condensate fraction is very large, above 90%, we say that is a superfluid kind of thing. Okay. The last one is of course the site number density. Site number density is the probability of occupation of a certain site. So that actually gives a visual picture of the vortices in the system. How do I know this is a vortex? Vortex is basically the density, what you call as the density deep, isn't it? In a continuum system, what I have is vortex means basically density deep. There is no liquid at the center, and there is a circulation around that. For discrete system, of course, I will not have a continuous thing, but I will see the occupation probability is from the scale of this thing you can see. In this case, the first one, there is no vortex. Why? Because the density D gradient is not there. Because yellow from that scale is very large. That means there will be more density at the center and then the density outside. Okay? On the other hand, this place, there is a vortex here. So you see that the density has changed continuously. Continuously changes, and from blue to black and so on. So this is the black one. So this is the lowest density. Okay. So this is my condensate density, which is the deep in the condensate density. So this is one of the vortex state by knowing the. So what you see that if you plot the position, then you will see at the center of this vortex, the 4 lattice will have minimum occupation probability. That means there is a density D. This is another vortex. Here, of course, it is not the black one, but blue with respect to its surrounding. So it has less density corresponding to its surrounding, which is yellowish or deep yellow, orange color. Okay. So this is another vortex. So how do I changing from this figure to this figure? By changing the frequency of rotation. And I know that if I change the frequency of the rotation, I get vortices, new vortices. Okay. So first vortex, second vortex, third vortices, because it's a 4x4 lattice. So I should expect 3 vortices. So this is the best picture to show you quantum vortex state in terms of density, and we can see that what does it mean, the density D. Similarly, we have done it for triangular lattice. For the triangular lattice, of course, it is more complicated figure. Because now we have more number of sides and more number of possibilities. Okay, so here is a picture where again from here, from the color, you see that there is no vortex here. There is a formula, just like for L cross S lattice, there should be L minus 1 vortices for a square lattice. For a, what you call it, the triangular lattice, the formula is something L minus 1 divided by 2. Don't remember it here, I have not written. But there is no vortex here. You see the maximum density. There is a vortex here because this is a bluish one. Bluish one is more or less compared to the surrounding yellow. Similarly, there is a vortex here, and a vortex here. So there we have 4 vortices. Okay. So these vortices at the center, these black ones, are here. Okay. This is one vortex. And the corresponding current, if it is a perfect vortex, you see that there will be no current flowing here like that. For example, this is a perfect vortex because the density is almost no particle is there. This is black, okay, almost no particle. And then there is a current flowing outside this one. So this is the boundary current. And what about these ones? These are some anti-vortices inside some vortex. Okay, so these are the possibility, different kind of. So I think I will conclude. Why basically I want to tell you here what we have obtained and what we have just obtained the vortex states. Okay, this is just the beginning of the study. We have to do the real physics study after this using this vortex state. So I will tell you what should we do. We have examined the effects of lattice geometries, interparticle interaction, and the spatial inhomogeneity on the quantum vortex states of the strongly interacting boson on 2-dimensional optical lattice. So main observation that we have obtained are the number of allowed vortices depends on the lattice geometry. Okay, for example, if it is a square lattice or L cross L, the number of vortices is L minus 1. If it's a triangular lattice, the number of vortices will be different. The maximum phase difference between the neighboring lattice sites depends on the lattice site and lattice geometry. Again, for triangular, and I've shown you the pictures, isn't it? They will be different. The variation of angular momentum with rotational frequency also depends on the lattice geometry. Again, because of the how many vortex will come inside the picture. The effects of 2 and 3 body particle interaction also depend on the lattice geometry. However, the particle host symmetry is present irrespective of the lattice geometry. Why I'm telling you most of the time lattice geometry? Because this is where we are going to do the future application. Because it's for different kind of lattice that we want to study. For attractive 2 and 3 body interaction, the angular momentum average and the total boundary current shows extra jumps. However, the jumps are not associated with any new vortex in the system. These states are usually squeeze states, phase squeeze states, and normalized variance with normalized variance greater than 1. The spatial inhomogeneity introduced by the harmonic trap potential leads to asymmetry number density. The number density picture that I have shown you is very homogeneous, okay, symmetric. But if I make my spatial inhomogeneity, that means if I put the trap potential center somewhere here, for example, then there will be deviation in the density distribution, and that is what is expected. All right. Strong interparticle repulsive interaction can reduce the asymmetry in the site number density. Even if there is a site number density asymmetry, but if I put strong interaction, then there goes. So this is important, what we want to do in future. Exotic optical lattice of various complex geometries like hexagonal lattice, leaf lattice, Kagome lattice, etc. have been created recently. Not much is known about the quantum vortex in such rotating optical lattice. But if you remember, those of you know about these lattice, leaf lattice, Kagome lattice, they are basically the combination of square lattice and triangular lattice. Okay, so what we have studied is the square lattice, rectangular lattice, and triangular lattice. So once we have, these are the basic building blocks of this more complicated lattice. So it should be possible for us to calculate what are the quantum vortex states in such exotic lattice. Okay. Now, already people have derived the Hubbard model on a honeycomb and Kagome lattice. So what we have done is that now, once they have done analytically some kind of ab initio calculation, gives you the Hamiltonian for Hubbard model on honeycomb lattice, Kagome lattice. So we can start from that Hamiltonian, because we have started with our own Hamiltonian. We can, for Hubbard and Kagome lattice, we can start from this Hamiltonian, and then this may be a good starting point to obtain the quantum vortex state in such rotating optical. So this is what has to be done afterwards. Now. But now we have basically, we know what to do. We have to just change the Hamiltonian. Our results are expected to be useful for understanding the parallels between the atoms in rotating optical lattice and the electrons in an applied magnetic field. In particular, interpreting studies on the bosonic version of the fractional quantum Hall effect in confining the optical lattice and co-rotating harmonic trap. So basically, these are the things that one has to calculate. How does the quantum vortex states or atoms that we have considered here, Bose atoms, confined to different kind of optical lattice, different kind of harmonic trap, how does they contribute to this kind of physics? And the last one is that, can I do a quantum simulation for this? And this is possible actually, because there are many work where they have the simple Hubbard model they have done with a quantum programming, like for example, QHash in Microsoft or QIQT in IBM computer, people have done for small lattice. So we have also done something here, but I don't have any result. So maybe next time I should be able to give something on quantum programming on Hubbard model. So of course, I don't think we can do this calculation for this as complicated model that we have considered here, but at least a beginning can be made in quantum programming. That's all, I think. Thanks a lot. So what about now? Is anybody there? Hello? Or I'm talking without, they are not hearing me, or where is my?
No, I can hear you. So
okay, okay.
So maybe I will ask questions. Thank you for your talk.
Okay.
So two clarification I need.
Yes.
So could you please explain benefits or applications or practical use of vortices quantum?
No, in this strongly correlated system, or in the usually weakly interacting system. Okay, let me tell you both. Okay, in the weakly interacting system, where we obtain the vortices by solving the Gross-Pitavsky equation and all this thing, no, it has got several applications. Like for example, one application. Actually, I was just giving a talk in the conference here on the same thing. How can you use vortices to study different physics problems? The first problem we discussed was the vortex that is melting in superconductor. So in presence of disorder. Okay. So I have the Gross-Pitavsky equation. I put the disorder in the system and I show that how the vortex that is melting happens. And this melting has been seen experimentally. So I compare it with my calculation. The second calculation is quantum turbulence. Okay. Quantum turbulence phenomena, where vortices are the main ingredients of quantum turbulence. And that's what we have studied in one of our recent paper in physical review A 2021, quantum turbulence using this one.
Mhm.
The other thing that we have done is that nowadays for gauge potential, okay, the application of gauge potentials or basically you shine laser light on that condensate and then you try to see that what are the artificial gauge fields that is created, and in presence of the artificial gauge field, how does the vortices changes in the systems and so on. Yet another thing is that how does we put impurity into this vortex system by changing some fraction of the condensate atoms. So these are for continuum. For discrete system, we have the similar thing, but we have to just see that how to obtain that lattices, and then how does it different quantities that I can calculate.
Okay, thank you. Last question, which parameter or term in Hamiltonian, which you consider, is responsible for formation of vortices?
The vortices are mainly because of the rotation, that QIQT term. See, I have put a rotation, gives a tunnelling term, isn't it? Tunneling term was there in Hubbard model from kinetic energy also, the T term. But because I have rotated it now, there is an additional rotational term, tunneling between from one side to another side. So they do add up actually, giving rise to rotation. Rotation and tunneling from one side to another. And that is the, when it completes one circle, that gives rise to vortex.
Because the Hamiltonian, which you have written in your presentation, and it is very similar to in nonlinear optics, and some terms are responsible for fourth order tensor and sixth order tensor. So the fourth order tensor is responsible for creation of Schrödinger cat states. So maybe you will see some cat states, but it is, I think, is like association of my associations with nonlinear optics, and that is why I'm just trying to understand.
Only thing we have to understand here, this is a discrete system, okay, compared to the optical that is, optical when you apply it in optics and all these things, these are usually continuum systems. Here it is completely discrete. So we have to redefine our quantities and see what are there.
Okay, thank you.
Thank you.
How about other questions? Because I have a couple of questions. You know, this by any chance, could you see this vortex binding, vortex anti-vortex binding? That is, of course, without a magnetic field, without.
Yeah, see, we have very much restricted, okay, because this is a Bose-Hubbard model. Number of states become 1 crore actually, 1 crore by 1 crore matrix, just for a 454 lattice with just 1 or 2 particles. And so we can at best create one vortex. For interaction, I have to create many very big lattice, and then I have to see the interaction. Okay. So basically, I should have at least 2 or at least 2, that is 3 vortexes, right? But we have only one of different phase winding, 2 pi, 4 pi, 6 pi, and so on. So this is not possible, but you can go to quantum Monte Carlo studies or renormalization group study and are in those things. Density matrix renormalization group. That kind of.
So you can actually, sort of, simulate a lot of things like, ITC Hubbard model, ITC ground state, and unique ground state.
Yes, exactly. Yes. So these are actually will be because high temperature, high transition temperature superconductor, the model is Hubbard model.
Correct.
But only, as I said, that with this, but people, what they are trying is that they are trying to put more on, instead of directly going to high TC, what they are trying to do here is that different optical lattice, like lead lattice, Kagome lattice, if I put them, how does the physics looks like, or what are those different quantities, mod to superfluid transition? Simple thing only they are studying, but on different kind of lattice. Okay, so that's why the idea.
Yeah. So honestly, I really enjoyed your talk. And if there are no more questions, let's thank Professor Dey for a wonderful talk. Thanks a lot, Professor.
Okay, thank you, Prasad.